Hello everybody, my name is Ever Barbero. Today I'm going to talk about fatigue. Specifically, we're going to talk about finite life. How do we calculate the life when the fatigue safety factor that we calculated before is less than 1. So less than 1 doesn't mean that it breaks, it means that it has less life. All right. So, in previous lectures, we calculated the yield safety factor, okay, and the fatigue safety factor, eta F. And so if the yield is greater than 1, that means that no yield occurs during the first cycle. That's what the yield safety factor checks. It doesn't check at n equal to 2 or n equal to 1000 or anything like that. It's just first cycle. It doesn't yield, you say, okay, it doesn't yield. So then for more cycles, the safety factor is NF for fatigue, eta F. If it's greater than 1, we have infinite life, okay? So if eta F is less than 1, the infinite life will not be achieved. And in this presentation, we see if we can calculate what life will be reached when eta F is less than 1. We already calculated this. All right, so basically what we do is we look at from the point of view of Moll-Goodman. We can use other interaction criteria to do the same. The formula a little bit different, but not much. So first we look at point A that has eta F equal to 1, barely infinite life. How do we know that? Because point A is on Moll-Goodman. All the points on this line from this one to this one have barely infinite life. That means eta F equal to 1. So for us, this is on our low line, and then here we have eta equal to 1. That means that any combination of sigma m, sigma a on the Goodman line, not this value but less, so that you go to a, and sigma a that goes to a, any combination like this, all right, like this, or any other combination like this, okay, will produce eta the same value, 1, and on the Moll-Goodman line. All right, so basically, if whatever I do, if I do here, this combination, eta is equal to 1. And I erase it, and then I say, okay, give me this combination, eta is equal to 1, because the point is there. So I erase it. All right, so now we go to point B. All right, point B has eta less than 1, which we calculated before in the previous video. All right, and so that means that it's going to have a life n, which we call n ReV for revolutions, n ReV less than infinity. We don't know yet how much, but we know it's less because it's on this side of the line. On this side, it will be more than infinity. I mean, more than infinity. If safety factor is greater than 1, so for sure it's infinity. This is safety factor equal to 1, barely infinity. Here, less. All right, so then in order to calculate the life, what we do is we draw a line from SUT, from here, through B, this line in red, and we extend this line all the way to sigma ReV, which we define. So this is a stress, a value of stress, because this is the axis sigma A, right, where sigma A's are plotted. These are the alternating amplitude components. Okay, and so so any point on this new line, on this red line, including the point 0 sigma ReV, which is this point here, but any other point, like point B, has the same eta F less than 1 that we calculated in the previous video. So let's say that's 0.8. So this point B has 0.8, this has 0.8, all of these points have 0.8, and even this point has 0.8, all right? So, okay, but what is important about this point rather than this point? At this point, I have a combination of two stresses, the mean value and the amplitude. And I don't have a formula to calculate the life when I have combinations of sigma m and sigma a. But I do have a formula to calculate the life when I have only one stress. That's why I move from here to here. For this stress is alternating. And how much is the mean? The mean is 0. So this stress is like the stress that we apply to the R.R. Moore specimen. It's an alternating stress, it has no mean, and for that we have a formula, which is the fundamental formula for fatigue, and the inverse of the fundamental formula is this formula here. And remember, n is just now is ReV. It's going to be sigma. What sigma is sigma ReV divided by A to the 1 over B. You remember this formula? This is the formula, is the inverse of the fundamental formula. And it allows us to calculate the life if we know the alternating stress, but it has to be alternating. I cannot put two stresses in here. I have room for only one stress, and it has to be alternating. All right, so why I put this sigma value ReV? Because this sigma value ReV is equivalent to this combination sigma m and sigma a. Because sigma a, sigma m will produce a safety factor less than 1, say 0.8, and this also will be 0.8, and this will be 0.8, and also there is going to be 0.8. And the nice thing is that this one has the same safety factor, but it's an alternating. So since it is an alternating only, I can put it in the formula here, and I can calculate the life. Okay, so that's basically it. If we want to do with another criterion, all we have to do is replace this line by another line or a curve and do the same, okay? But the easiest, of course, to explain is with Moll-Goodman because it's a line, all right? Okay, so then we have a formula for the number of revolutions that the part can take when it's subject to sigma ReV, which is equivalent to this combination sigma m, sigma a. Equivalent in which sense? In the Moll-Goodman sense, all right? Because we use Moll-Goodman for the derivation. Okay, so now the question is, how much is sigma ReV? Well, okay, if we do it graphically, like in the old days, this is log plot, so we have to get log paper, draw all this thing, and then, of course, you know, we have our log line, we know point A, we know point B, because this is our sigma M and sigma A, which we know, and then we draw this line, okay, with a ruler, very nice, and we go there and we take this value, and according to this scale, we get this thing. But I don't have log paper, and you cannot find log. I couldn't find log paper anywhere, so we gotta use equations. All right. So in the next slide, we get the equations. Okay. So sigma ReV we can get graphically or with this equation like this. Okay. And so how do I derive this equation? Well, I take the equation for Moll-Goodman, right? And the equation for Moll-Goodman, you remember it has inside an SUV. You have to remember this. I'm not going to write the equation for Moll-Goodman again. Okay, but inside the equation for Moll-Goodman, which is very easy, there is SC. And then you say, well, no, I don't want SC because I don't want the black line. I want the red line. So you substitute sigma ReV for SC in the equation. And once you do that substitution, then since you know everything else, then you know sigma A, you know sigma M, you know SUT, then then you get sigma ReV out, and it's this equation over here. Very nice, very simple. And it's nice to do this because if you want to derive the equation for some other criterion, say Gerber, you can do the same. Substitute sigma ReV for SE, and then take sigma ReV out, and you get your own equation. So then once you have sigma ReV, okay, this equation we know from the previous slide, is the inverse of the fundamental equation. We can calculate the life. So with that, we can do an example numerically. We have a steel bar that has SUT 80, SY 65, and SE for the component already calculated 40, and they even give us the F. So all the hard work is done. And it's subjected to fluctuating stress, fluctuating because it has maximum and minimum. Okay, this is interesting because the maximum is positive and the minimum is negative. Okay, so calculate this life. So first we calculate with Moll-Goodman, get the safety factor. All right, so the sigma amplitude prime from Moll-Goodman, you remember, is the minimum minus the maximum. Okay, but the minimum is, no, the maximum minus the minimum. The maximum is 60, the minimum is minus 20. So minus plus, I get 40. And sigma m, it was maximum plus minimum, but minimum is minus 20. So you get 60 plus minus. Divided by 2, you get 20. Right here, when you get the mean value, okay, then you want to make sure that this mean value is less than SUT, because if the mean value is greater than SUT, then it will fail. But it's less because SUT is 80, so we're good. And once you have these two values, oh, here it is, the formula for the safety factor for Moll-Goodman. Prime over SE, prime M divided by SUT. So calculate this. Sigma A is 40, I got it here, put it there. SE is 40 from here, I put it here. Then M is 20, put it here, and SUT is 80, okay, put it there, to the minus 1, oops, 0.8 is less than 1, the life is finite, all right? And in this picture, of course, you put it there because to remind you what all these things are, right? When you have, you say sigma maximum what it is, okay, here's sigma maximum. Sigma minimum what it is, here's sigma minimum, but in this case it's negative, so it's somewhere here down here. All right, and then you get your amplitude, which is this, which I call it prime. All right, and then you get your mean value here. Okay. All right, so we got that. So we got this safety factor less than 1. So let's see if we can calculate what the life is. And so now what we have to do is, okay, this is the same thing, the properties I put again. Check that sigma mean is less than SUT. Yes, we check, it's done, so it's not gonna break. Okay, so sigma revolution, this is the formula that I showed you before. Yes, yes, written in a slightly different way. And then, so I replace sigma A from the previous slide is 40, minus 1 minus sigma M, previous slide is 20 divided by SUT, which is 80, to the minus 1, I get 53.33 kpsi. So the value of sigma rev, yes, is greater than SE, all right? So if SE, which is how much it is 40, okay? Say this SE here is 40, and the sigma revolution that I calculate is 53. Okay, so maybe 53 is here, say 53. All right, so the stress that I'm putting there with sigma REV is 53, but SE is only 40, so this SE is 40. Okay, so if my stress is 53 and SE is 40, I cannot expect infinite life. Yes, we know that. Safety factor 0.8, I cannot get infinite life. 53, of course, I cannot get infinite life because too much stress. But right from the graph, I can get the value of the life. All I have to do is go down here, and that's the number REV that we're looking. So you see with the graph, in the old days with log paper, it's very easy. You just can look at it. It's there, boom, you come down, that's the life. We gotta derive an equation so we don't have to do the thing on paper. Okay, so in order to calculate what the life is when we enter with stress, well, we've done this before, right? You enter with a stress here, which in this case is gonna be sigma REV, which is 53, you come down and you want this number, right? So in order to do that, we need to calculate A, and we need to calculate B, the slope. All right, we have equation for that from previous videos. A, F SUT squared divided by SE, so F is 0.9, SUT is 80, SUV is 40, square, 129. And B, minus 1/3 log F SUT over SE. Okay, F is 0.9, SUT 80, SE is 40, so we got that. So once we have these two numbers, then we use what will be the inverse of the fundamental equation for whatever stress we calculated, which is 53. So we put the 53 here, and A and to the minus 1 like this. B, yes, correct. And then we get 34,000 cycles. So this number here, according to this equation, is 34,000, this number here. Okay, so with that, I think we're done. All right, so to summarize, if the fatigue safety factor less than 1, the life can be calculated, all right? So how do we do that? First, we calculate the value of stress sigma REV that has the same fatigue damage. I introduced this thing about fatigue damage because, you know, it is not broken, but by a certain number of cycles, it will be 34,000, it will be, all right? And it has the same damage as point B. So what we do is really, we introduce this value of sigma REV, which is equivalent to point B, but instead of being taken over to this number of cycles by sigma M, sigma A, we say, okay, just put sigma REB, purely alternating. Anyway, both are on the same line, all right? And then, so they have the same amount of damage, and then it will fatigue at the same time. And so, as point B. And then we use a fundamental equation, basically the inverse of the fundamental equation, to calculate the life N, and we're done. Okay, so so I think that's it for fatigue for this series of lectures. There are other things about fatigue, metal fatigue. Yes, there are more topics. Not complicated, but not really too complicated. It's just that it's getting long, and I want to stop. Okay, maybe in the future I make more videos. And then, of course, when you go to fatigue of materials that are not isotropic, not metals, like composite materials, then it's a different ball game, and there is room for a lot of videos. But for now, we're going to call it quits with fatigue at least. And all right, as usual, the videos are here or here, the homework is there, and I'm working on the app. Okay, so okay, it's coming. Okay, thank you very much.